Hey everybody. Today we're talking about the variance and standard deviation of discrete random variables. Each of these things measures the spread, or variability, of a random variable, with a variance being more convenient mathematically, but standard deviation being easier to interpret because it's on the same scale as the random variable. In each of these formulas, as you look at them, the thing in parentheses is representing how far an individual value is from what was expected, x minus mu sub x, where mu sub x is the expected value. So we take each of those individual deviations from the expected value, square them, that makes them positive, and then weight them by their respective probabilities. So here f of x is the probability mass function of the random variable. Add that up over all the possible values the random variable can take. That's your variance. Take the square root of that. That's your standard deviation. These definitions are often written in terms of expected value. So for variance, we're talking about the expected value of x minus mu quantity squared. Remember, the expected value of a function of a random variable is just the weighted sum of the values that that function takes over all the different values the random variable can take. This formula is particularly helpful in proofs and other applications because we have a lot of properties of the expected value that we can leverage in those proofs when we use this formulation. Here's an example. As always, I recommend pausing the video, trying this computation before seeing my solution. We have this random variable x. It takes 5 values. We have their respective probabilities as described by this probability mass function. To get the variance, we're first going to compute the expected value, basically taking the weighted sum of all of the different values the variable can take. So we've got 60 times 0.22 plus 70 times 0.14, etc. We simplify that, we get 77.8. So on average, when we take a draw from this probability distribution, we get 77.8. We then compute the variance by taking each of those individual x values, subtracting off 77.8, squaring the result, and multiplying by the respective probability. So 60 minus 77.8 quantity squared times 0.22, etc. After we do all of that arithmetic out, we get a variance of 145.2. We can also take the square root of that to get the standard deviation, which in this case ends up being about 12.0. Roughly speaking, the standard deviation of x is the average amount by which a random value from the distribution will differ from its mean. So in this example, on average, the results are going to be 77.8, and an average draw from this distribution will differ from that average by about 12 units. Usually, most results fall within one standard deviation of the mean. So this histogram, this probability histogram, is drawn for the distribution that we've been looking at. And I've labeled the mean, the expected value, at 77.8. And then I've gone one standard deviation below that and one standard deviation above that. So down by 12 and up by 12. And you can see here that most of the results in this probability histogram do fall within one standard deviation of the mean. And that's a pretty solid general rule. For bell-shaped probability histograms, things that are similar to a normal distribution, that proportion is going to be closer to 2/3. Now, in general, you don't want to do these calculations by hand in this day and age. I use R for my calculations, and so here's some example code showing how you would compute expected value, variance, and standard deviation using R. And one thing that's pretty well universal when you're coding this stuff is that the code you're going to do is going to directly reflect the formulas. So, for instance, as you look at the computation here for expected value, the sum of x times p, that's exactly the formula for expected value that I had on the slides a little bit ago. Similarly, for variance and standard deviation, the code directly mirrors the formulas. Variance has some very helpful mathematical properties. In particular, if x and y are independent random variables, so the outcome of one doesn't give you any information about the outcome of the other, then the variance of the sum is the sum of the variances. And for any random variable x, the variance of a constant times x is that constant squared times the variance of x. So you just have to be a little bit careful when you factor out that constant that you also have to square it as you factor it out. In other words, it's pretty easy to compute variances of linear combinations of independent random variables, although variance is not exactly a linear operator. Taken together, these two facts imply that the variance of a difference is the sum of the individual variances when x and y are independent. In other words, subtracting independent random variables increases the variance, increases the variability, rather than decreases it. There are formulas for standard deviation as well. When x and y are independent random variables, you can find the standard deviation of the sum of those two random variables by doing a sort of Pythagorean theorem on the individual standard deviations, squaring them each, adding them up, taking the square root. Also, if you want to find the standard deviation of a constant times a random variable, you can factor that constant out as long as you take the absolute value, basically making it positive. And that's reflecting the fact that standard deviation always has to be positive, but the constant doesn't necessarily have to be. An important fact that's really helpful when you're computing the variance of a random variable, and therefore when you're computing the standard deviation. The variance of any random variable is equal to the expected value of x squared minus the expected value of x, quantity squared. This is important because this formula is almost always more gentle to use when you're doing calculations of variance and standard deviation than the original definition. The proof is direct and I think pretty typical of proofs that involve variance, so I'll just flash it really briefly. We're going to use the definition in terms of expected value and then FOIL out that square, the x minus mu quantity squared. Use the linearity of expected value to break up that expected value into three pieces. And then notice that mu is constant as far as the expectation is concerned here. It's just some number. So that can get factored out of the expected value. After we've done that, we can rewrite e of x as mu. So the middle term becomes minus 2 mu squared. And the last term is just the expected value of a constant, mu squared. So the expected value of mu squared is just mu squared. Simplifying a little bit, writing mu as e of x again, we established the theorem. So, for instance, going back to that original example with that same distribution we had earlier, where x can be 60, 70, 80, 90, or 100, with the probabilities listed here, it's almost immediate to compute the square of x, the squares of the different values that x can take. When x is 60, x squared is 3600, for instance. And so finding the expected value of x squared is really quick. 3600 times 0.22 plus 4900 times 0.14, etc. So the expected value of x squared is 6198. To find the variance, we do 6198 minus 77.8, the expected value of x that we found earlier, squared. We do that arithmetic, we get 145.2, which is exactly the same result that we got earlier.